Okay.
Yeah, you test.
Yeah, because now I can't see you at all. So let me.
Yeah, I've started the stream. Yeah.
Okay. Okay. Everything is okay, right? On my part, you can see my title slide.
Yeah, I can see, and also your slides are working.
Okay.
Everything is perfect.
Okay. So you just let me know and then I'll begin.
Yeah, let's see. For 1 or 2 minutes, we can wait.
So how will it work if somebody has a question? You will
Uh,
just.
I I uh, I assume they can, if they have any question, and I'm thinking that they may not only have question regarding the work.
Mhm.
It's fine with you, right?
Yeah, yeah, that's perfectly okay. But I can't see anything beyond my screen at the moment. Uh,
Yeah, you
so
won't see anything beyond your screen.
yeah.
Do you need to, if you
No,
want
no.
to
So if
add
somebody
anything
types in a
regarding
question, I won't be able to tell. So can you
yeah,
stop
I
me?
will let you know whatever is there.
Yeah.
But I think it is better we have questions at the end
Mhm.
so that what you want to convey doesn't get interrupted.
But I'm perfectly okay if somebody wants to ask a question in between.
Okay,
So
sure.
yeah,
Yeah,
because sometimes it's easier. I think that something is intuitive, but
sure. I will
maybe.
message it out. Sure. Okay. Yeah. So we have yeah, people joining.
Okay.
Uh, Hi, Karthi Ganesh. Uh, Ayan
Hi
has also
Chetan,
joined. Hi.
KG here.
Yeah, hi. Ayan has also joined.
Yeah, let's wait for a few minutes. Yeah, great.
Let's wait for a few more minutes then.
Yeah,
Yeah,
sure.
sure.
So maybe we can introduce each other for the
Mhm.
start. I'll introduce Rutvij like formally, but whoever has joined, maybe KG, you can start.
Yeah, sorry. I was with and
Yeah, I
close,
understand.
just muted. Yeah, my full name is Karthik Ganesh. You can call me KG. I am working as a chief quantum architect in Boson QSI. Following the quantum technology since 2004, did a master project in 2010. Actively involved in quantum computing career since 2019. I also one of the founder of Quantum Computing India. Yeah, this is a short introduction about me. Passionate about the quantum computing. QML is my area. Cryptography is my one of my weakness. But that's the reason I wanted to understand and then join this session. Yeah,
Yeah,
thank you.
yeah. Thanks for joining. Yeah, Ayan, if you can. Uh, and
Hi. Sorry. Well, my voice is a bit shaky. So,
yeah, yeah, we, yeah, yeah, go ahead.
yeah. So I currently working as a research engineer in Center for Development of Telematics, which is under the Department of Telecom of Government of India. So actually here we are in mission to create quantum key distribution systems that can be readily deployable in Indian standard existing networks. So, and I did my PhD from Physical Research Laboratory, India, and my work mainly revolves around in experimental realization of quantum cryptography and quantum communication mainly. So that was a brief thing. Thanks, Chetan.
Yeah, thank you. Mahima, if you are able to connect.
Yeah, hi. Hi, Chetan. Hi, KG. I know him as well. We know each other through QZI. So yeah, excited to listen the session. And I am a PhD scholar in IIIT Kottayam, and my current research is targeted on uh, quantum resistant cryptography, more of applied cryptography. So yeah, which looks for hybrid systems like applying QKD and PQC, like post quantum cryptography. So more of applied cryptography rather than like building from scratch. I'm looking forward to develop like core solutions as well. So yeah.
Yeah, and also we have a few of my colleagues from IIT Roper. So Shilpi and Monirul and Jatin and Ratnakaran, they all are my lab mates, like colleagues in this at IIT Roper. Yeah, they are working on different things. Like, yeah. If anyone wants to introduce yourself, yeah, please go ahead.
Yeah, hello. So this is Ratnakaran. I'm working under Dr. Ashoka Biswas in the topic of open quantum systems. So particularly on the quantum heat engines rather than many body physics. So that's the direction in which I'm working. So Dr. Chetan Ogela is my senior. He worked in our lab. Thank you.
Okay, I think then we can start. It's around 10 minutes from 11. So, yeah. So I'll introduce Rutvich, and also before starting, I would like to thank him for accepting this invite. Uh, so he completed his bachelor's from IIT Kanpur in physics, and then he finished his master's in theoretical and mathematical physics from Imperial College London. And meanwhile, he also worked as a research assistant at TIFR for like 10 months. And he finished his PhD from University of York in UK. Uh, and now he's currently a postdoctoral researcher at QIT at KAIC in South Korea. And his interests are in quantum information and foundations of quantum mechanics. And so, again, I would like to thank him for joining and uh, enlightening us with his expertise. Yeah, thanks.
Thanks, Chetan. Yeah, so okay, so actually, the audience that I had in mind were sort of like non-experts, undergraduates. So I'm sorry if this is a bit basic for the people in yeah in the chat right now. Uh, but feel free to ask me certain questions. The topic is a bit, so the topic that I'm going to talk about is on device independent cryptography and randomness expansion, but I'll mostly focus on device independent randomness expansion because that is primarily what I do. But again, what I like the core principles of device independent randomness expansion are exactly identical to the core principles of device-independent quantum key distribution, except there is one extra step of privacy amplification and error correction, but everything else remains the same. So hopefully we can understand device-independent randomness expansion properly, and then we can also talk about device-independent quantum key distribution later on.
Okay. So before we go ahead, so by device independence, you mean that there is nothing that can be, no information can be taken out depending on the device that we are using.
Yes, I will motivate what exactly do I mean by
cryptography.
yes. Yes, so I will motivate what device independent protocols mean, what device independence is.
Sure.
But yeah, so I am primarily a physicist who happens to know who picked up a little bit of information theory during my PhD, and so my primary interest is in quantum foundations and foundational topics in quantum mechanics and how to apply them in cryptographic scenarios. And so the topic of device independence is exactly the right place, because device independence sort of looks at very core fundamental quantum foundations questions like non-locality, intrinsic randomness, contextuality, etc., and applies applies them to do certain practical protocols. So today, what I will be talking about is, as I said, device-independent randomness expansion. So without any delay, let's begin. So again, I think the audience in this for this talk knows why we need random numbers for cryptography. But in case people don't know, then here's a very short motivation, or very rough, vague motivation of why we need random numbers in cryptography. So imagine you're going to a shop, and you want to buy something using your credit card. So every time you use your credit card, you have to basically, you plug in your credit card to a machine which somehow talks to your bank, tells the bank your credit card number and other details of that is transaction amount, etc., and your bank has to approve or deny your request, right? And so you need to send information, very crucial information like your credit card number, etc., for your bank to verify. But now the main problem in cryptography is that how do you send this information via, in such a way that only your bank can actually listen to it and nobody else can listen to it. And so a typical way is to construct these keys, which sort of unlock your data, lock your file. Then you send that file via any channel, and then you unlock your file via the key that the bank has. And so because you and your bank only have the key, only you guys can talk to each other, and only you guys can see what is in the data. Okay, and the way this key needs to be generated is using random numbers. So random numbers, or generating random numbers, is at the heart of quantum cryptography, and we need random numbers to do any kind of quantum key distribution to start with. Okay, and an important thing here to note is that if anybody else has the access to same random numbers as you guys have to make keys, you and your bank has, then they can also make a key for themselves, and they can also start reading the data. Okay, so you really need random numbers to do any kind of cryptography. Okay, so hopefully I have convinced you that using random numbers is essential in cryptography, and it has other applications in certain scientific experiments, etc. Okay, and therefore to do cryptography, we need a source of random numbers. Okay, and this opens up a fundamental question: how to build a random number generator. Okay, so before I try to define what a random, before I try to talk about how to build a random number generator, I'd like to actually define or give you essential properties of what random numbers are. Okay, so the first property is that these numbers are unbiased, that is, they are distributed according to uniform probability distribution. And second, and more importantly, they are secure, meaning nobody else has access to them. Nobody else can guess them. So they are unbiased for everyone who is trying, for every entity, every possible adversarial entity. Okay. So these numbers are uniform or random for everybody who tries to guess them. And now this is a difficult question. Generating unbiased unbiased numbers is not as hard as actually certifying whether the numbers that you have are secure or they're unguessable to anyone. Okay. And so, what is a typical way? If I ask you how do you build a random number, you say, okay, I'll start tossing a coin and looking at its output. But if you look at tossing a coin, if you see it very carefully, it's a classical process, and therefore it is fundamentally deterministic, meaning that if somebody has access to certain initial conditions, they can predict with certainty what your outcome is. Okay, in most scenarios, you might not have all like a full idea of your initial conditions, but even having certain partial idea, some partial information about the initial condition is enough to guess with a reasonable accuracy what the outcome is going to be. Okay, and when your credit card machine is talking to your bank, there is not a human who is tossing coins. There is typically a machine which will be tossing coins, and now you have these machines could be using for biased coins. Okay, and you never know if these coins are designed in such a way that they are very likely to land on one face than the other. Okay, so basically, either you using a classical process, in principle you can determine it fully, but in practice you can determine with a high accuracy as to what the outcome is going to be. And when you know something with a high enough accuracy, what you can do is actually, without going into too much details, you can predict part of the key that is used to generate this random key. You can predict part of this key, and when you start predicting parts of each key, these are also dangerous because you unlock some information about the key. And if your credit card is used often enough, from some information you can patch everything together, get all information. Or sometimes you want to not even reveal some part of the information. So basically having classical process is hopeless. So we need a truly quantum process if we want truly random numbers.
Sorry to interrupt. So are there any examples where they have hacked or they have kind of broken into the random number generator and
very famous. Very famous. I think this NIST NIST had recently in 2010. They had these NIST certified random numbers, random number generators was based on some elliptic curves, etc. But they had a backdoor key to it, and so NIST, the American government, was actually reading all the encrypted emails or whatever, encrypted data. So it was very recent, in 2010 this happened. This has happened in the past. Right. So this is not something hypothetical also. So we need to really know how to generate random numbers if you want like a lot of privacy. Okay. So we need to, I was basically motivating that we need truly quantum processes to actually generate these random numbers. But now the question comes as to how do I know whether the process that I'm using is fully quantum? So I need a quantum random number generator, but how do I certify the Q out of the QRNG? Okay. So you say, okay, I can go to a manufacturer and buy a quantum random number generator. Some manufacturer sells it. There are lots of manufacturers that sell it these days. And I can do a statistical test. So I can run this quantum random number generator for some time, check if the outputs are uniformly distributed. Once I'm happy, I'm okay. But actually, you are still checking for the uniform randomness bit. You are not checking for security. Because what essentially could have happened, or the easiest way, is that the manufacturer has access to a secret memory, Now, these are all numbers which are uniformly generated, and the manufacturer has very smartly placed it somewhere. So what essentially happens is, for show, he's showing you, or they're showing you like a big, complicated device using certain things. But at the end, your numbers are coming out from a secret memory, which already your manufacturer has access to. So now, even though they have, in principle, sold you a quantum random number generator, there is nothing quantum of happening there. So so you can't just go to a manufacturer, say, I want to buy QRNG, and you can be sure that you're actually buying a QRNG. So what do? You say, okay, I open up my QRNG, I check for each and every component of the QRNG, and model everything, and that's how I be sure. But again, that's really, really difficult, because your manufacturer could be very smart, you don't know, and also this may be impractical, if not difficult. Okay, so that's not a way. Another solution you might offer is that, okay, I'll make my own quantum random number generator. But again, you have similar questions. You are buying certain things from your manufacturers. You will buy certain components. If not, then your whatever random number generator you have to check whether it's doing exactly what it is meant to do at every given step, which may be difficult. Okay, so what do? It seems like generating random numbers is really hopeless, and we can't do anything about it. But fortunately, there is some solution to it. At least there is a partial solution to it. And in my opinion, this is sufficient. And the solution is as follows. There are protocols called device-independent protocols of randomness expansion, which take a very small seed of random numbers, input random numbers. It is very small seed. It could come from some, some source which we have full trust on. And then using that very small seed, you can get as large as you want a seed of, like, as large as possible a seed of random numbers. Okay, and this is done without trusting inner workings of the devices. So you do not put any trust on what's happening in your device, and you can do the same, whatever I said for randomness expansion, you can do the same for cryptography. So you can also do entire cryptography without putting any trust on the inner workings of the devices. And those protocols are called device-independent quantum key distribution protocols.
So the seed is also generated randomly from somewhere?
Yes. So again, there are how do we get seeds is a question which is true for almost all protocols, because there is this randomness extraction step that needs some seeds, etc. So barring that question, which will come for every protocol, you will need this initial seed. So if you have a small seed, you can get a large seed. Where do you get your initial seed is a question. There are part answers to this, also device-independent answers called device independence randomness amplification. So if you have some min entropy sources, then you can amplify the randomness in a device-independent way. So that's how you might get your seed. You might get your seed from cosmic microwave background radiation data. So okay, that small seed is needed, and that is one-time investment. Once that one-time investment is done, you can actually get as much randomness as possible. And yeah, a solution could be this CMB data, which nobody could predict. Okay? Your adversary might not be as powerful. So cryptographic assumptions need to be made, in the sense that there is this adversary who does not have full access to it. And of course, every time if you want to use your credit card, you actually set up some CMB, get cosmic microwave background data is not practical. So this is a solution.
Maybe from weather also they use?
Yeah, again, from weather also there are certain, there is some unpredictability. So here the assumption is your adversary you have access to. So for this talk, the assumption is you have access to a very small seed of random numbers that is not accessible to your adversary once the protocol begins. Sorry, before the protocol begins. After the protocol begins, or even at some point during the protocol, if they learn some parts of inputs, they're fine. But before, so whenever your adversary had supplied your devices, After that, if any, after that, these inputs can be known. Okay. So this seed can be known to this adversary after they have supplied you the devices. Okay. But before then, there is no hope. Okay, and there are practical ways. There are other randomness amplification protocols as to how you can get this seed. But for now, this seed is how to get this seed. I'm not dealing with this, and therefore I'm saying that there is a partial solution. So given some randomness, you can produce as much bits as you want without trusting the devices. How do you get this initial seed? That's a question for some other time. Okay. So yeah, this is, imagine you have 10 rupees. I can give you 1 million rupees, but how to get those 10 rupees? I'm not answering. Yeah. Okay. Right. So before I actually talk about device-independent protocols, I will talk about a game. This is called a non-local game. It's a 2-player game and it's a cooperative game. So 2 players in cryptographic scenario are typically Alice and Bob. So I'll stick with Alice and Bob. I wanted to give some Indian names to these people, but unfortunately I'm so used to Alice and Bob, so I'm not giving any Indian names to them. So for this talk, there's still Alice and Bob. They are not talking to each other. Okay, so the assumption is they don't talk to each other. And the way in physics we implement this assumption is we make them spatially separated. So Alice and Bob are far away. You can think of them as being on 2 different planets. Okay, and they're so much far away during the entire game that for the duration of this game, they, even if they want to try to communicate with each other, they can't, because they're space-like separated during the event. Okay, so right, so they're non-communicating parties. If you don't understand what space-like separation is, you assume that they're non-communicating. Okay, and now these non-communicating parties are given some questions. They're asked some questions. Now these questions are asked in such a way that this party does not know the question asked to Alice, and Alice does not know the question asked to Bob. Okay? And this can also happen because they are space-like separated. So you can generate these questions from the causal past of Alice. You can generate these questions from the causal past of Bob, which is not the causal past of each other. Okay. So barring them, like, this is possible. Physically, this is possible, asking these questions. Okay. And now what Alice and Bob have to do is they have to answer these questions, and they must give an answer. Okay. If they refuse to give an answer, you don't allow that. So they must give an answer. And the way we encode these questions is using a bit. So it's a number x 0 and 1 and y 0 and 1. So whenever Alice gets sent x equals 0, she knows that question 0 is sent. Whenever Bob gets asked question 1, he knows that whenever Bob sent y is equal to 1, he knows that question number 1 is being sent. Okay. And they are yes/no questions, so they have to output 0 or 1. Okay. So if Alice wants to say yes, answer yes to that question, she will say 0. And if no, then she'll say 1, and same for Bob. Okay. And you can swap yes or no, like 0 and 1, yes or no. Some people might prefer giving 1 as yes. That's fine. Okay.
Yeah, is it something like where you have a Hadamard gate?
Right.
And you pass a superposition and the wave function collapses to either 0 and 1.
So we are not talking about any wave function. It's a simple game, okay? And yeah, I will come into how this is a quantum game, but yes, there are, as you say, this collapse, etc. You can. But at the moment, it's a very simple game. I'm not talking anything about quantum mechanics yet. Okay. And so now the rules of the game. So how do you win the game? So this is a cooperative game. So either Alice and Bob win together or they lose together. Okay. And the way they win this game is if the product of their questions is the sum of their answers. So for example, if Alice and Bob are both asked the question 0, then they have to agree with each other. So they either have to say yes or no. Okay. Simultaneously. So Alice also has to say yes, Bob also has to say yes simultaneously. Alternatively, if they're both asked question number 1, then they have to disagree. So if Alice says yes, Bob has to say no, and if Bob says yes, Alice has to say no. Okay, so this is how they win the game. And if they don't win the game, you lose the game. So it's, again, you either win or you lose. There is no draw or something like that. Okay.
That symbol is for modulo 2, right?
Yeah, this is modulo 1. Yeah, these are all bits. So this is all, everything is mod 2. Okay, product is also mod 2. I mean, but that's evident, 0 and 1. But yeah. Yes. Okay, so how can Alice and Bob play this game? They can design some fancy devices which take an input and give you an output. And so at some point, Alice and Bob could have met in the past, could have designed these devices, could have used most fancy equipments to design these devices. But yeah, in general, we'll assume that they have some device that they have pre-programmed. Okay, they could have pre-programmed. So it could have some classical resources, some quantum resources, some shared randomness. They can have anything that they like. And they have to be pre-programmed in such a way that you maximize winning this game. Okay. But because these devices are with Alice and Bob, they cannot now talk to each other because they are again space-like separated. They could have talked to each other in the past, but now they can't talk to each other while they're playing the game. Okay. So what is Bell's theorem in this context? And here's the key punch. So if Alice and Bob were using classical resources to play this game, and only classical resources, they could not have won this game with a probability 3/4. So every 3 out of 4 times they can win this game, otherwise they will lose the game. So, but just saying how often they can win with a classical resource is not enough. You also need how well you can win with a quantum resource. So it turns out that if Alice and Bob were using some entangled quantum resource, then they can win this game with a probability of at max 0.5 plus 1/2 square root 2, that is about 85%, which is strictly greater than 3/4. So now you know that the set of strategies that Alice and Bob can use using quantum resources is strictly larger than the classical resources. And therefore, quantum mechanics is not compatible. I mean, the way it's often said is that quantum mechanics is not fully compatible with the classical theory.
Sorry to interrupt. So on the YouTube, someone has asked, is this prisoner's dilemma?
I'm not sure what a prisoner's dilemma is.
Wait, one thing. You can continue. I'll share the link to this. I made a mistake. I didn't send it on this thing.
I'm sorry. Yeah.
Continue. If there's a question, I'll stop you.
Okay. So now let's look at the converse of the Bell's theorem, which now is now useful for building our device-independent protocol. So the converse is as follows: if these inputs or these questions were randomly asked, and Alice and Bob won this game with a probability greater than 3/4, then the devices must have used a quantum process to generate outputs. Okay, this is Bell's theorem. And therefore, these outputs A and B cannot have been predetermined. Okay. And if you are a physicist, you might have seen Bell inequality, which looks something like this, which is in terms of expected value of this plus minus one operator, plus minus one valued operators. But this is identical. This is just what I have said in terms of this non-local game. This and this are to exactly the same conditions. They're just formulated in a different way. Okay. Right. So Bell's theorem basically allows us to gives us a certificate of whether I have used a quantum resource or whether I could in principle have also used a classical resource. Right. So now this is so now we know that, if you see a Bell violation, or if you win this game with a probability greater than 3/4, then you must have used a quantum resource to generate these numbers. So the outputs contain some kind of randomness. But now I want to quantify what randomness is. Okay, and so in cryptographic scenarios, the way you quantify randomness is the way you do it traditionally is you bring in an adversary. And the job of this adversary is to try as best as to guess as best as possible what these outputs of Alice and Bob are. So what Alice and Bob are saying, it's the job of this adversary to guess. Okay, and this adversary can know exactly what Alice and Bob are doing. So they can have information of what these Alice and Bob's black boxes are doing. They can also have something that is entangled with Alice and Bob's system in general. They can, and they can also decide, in fact, what these devices should be doing. Okay, but they are not in Alice and Bob's planets. So in cryptographic sense, they are not in the lab. So they can't directly talk to the devices because Alice and Bob's labs are shielded. Okay. Right. So the way you quantify randomness is using something called mean entropy, which is defined via some optimization problem. And this is a semi-definite program for computer scientists here. This is defined via some STP, and there's a lot of convex optimization in terms of how it is. But for this talk, I'm not going to define exactly what mean entropy is. What I want to tell you is an intuitive definition, and which is actually they're both identical. And the definition here is the mean entropy measures how well this adversary, which is very powerful, it measures the probability of this adversary guessing my outputs, the best optimal probability of this adversary guessing your outputs. And now that's a probability. If I take a log of this probability, I get the output in bits. So they're identical. But there is a more technical definition of mean entropy, which is given in terms of optimization problems. Okay, so now let's look at some special scenarios. So here's a special scenario. And this is a theorem, which says that if Alice and Bob win this game with this maximum probability that I said, half plus 1 over 2 square root 2. If in an experiment, if they actually win with this maximum probability, then Alice and Bob must have played this game with a single strategy. So it is really powerful. So you exactly know what Alice and Bob's devices are doing just by measuring their success probability. Okay. And now this special case is actually very essential because this strategy is such that this eavesdropper is completely uncorrelated with Alice and Bob. So basically your eavesdropper is just sitting on the side, and for all practical purposes, they're doing nothing because Alice and Bob's unique strategy just involves an entanglement between Alice and Bob and nothing else. Okay. So if you observe, if Alice and Bob play this game with this probability, then you can show that Alice gets 1 bit of randomness every time she plays this game. And you can construct some other special case scenarios also, but I'll be talking about the most general scenario from now onwards. But this was just to give you an idea of some special case scenarios. Okay, so let me now build a protocol, a device-independent protocol of randomness expansion. So in a lab, which is secure, put 2 non-communicating devices and make sure that they don't talk to each other. So you can shield them. You can also have them space-like separated. People have done this in their labs. Actually, in China, it was recently done. So it's possible to do it in one lab. So have them space-like separated, and then start asking them questions, yes, no questions. Ask the devices to generate yes, no answers. Do this a large number of times, enough number of times so that you get statistics. And after you get all the statistics, calculate the frequency with which Alice and Bob win. And if you have done it for a large number of times, you know using central limit theorem that frequency is actually the probability of them winning. Okay, so they're the same. And so once you have collected all the statistics and once you've calculated all the winning probabilities, you ask yourself, how have you won this game with a high enough probability? If you have not won this game with a high enough probability, say you won it with a probability less than 3/4, then you say, no, I'm going to abort the protocol, meaning I know that this protocol in principle could have been not secure. So I'll discard everything, inputs, outputs, everything, and I gain nothing. Okay? But if you have actually won this game with a probability greater than 3/4 or with the desired probability that you have set in advance, then you send your inputs and outputs for some process called randomness extraction, which is some classical pre-processing, which removes out all sorts of correlations and just extracts a random string R from your outputs and inputs. And now this random string R you can actually use to generate randomness. And now the main question that I asked during my PhD, and I still continue working in this, is that how much randomness you can get as a function of this winning probability. Okay, and now that is a difficult question to ask, because all I'm checking is how well your devices have actually won this game, how much, what is the probability of which these devices have won the game, and they could actually be using some iterative strategies, and every round they're using some different strategy, etc., etc. All I know is that they are random. I don't know how much randomness they're producing per round. So very quickly, giving you the results of what I did during my PhD. I know this might not mean anything to you, but so I've plotted frequency of winning this non-local game versus random bits generated per round of the game. So if you're playing this game for, let's say, 1,000 rounds, then multiply this number by 1,000, and this is your randomness. Okay, this is the randomness you can get out of the data. So as you see, if you're at 0.75, that is 3/4, then you get nothing, because there is a classical strategy with which you play the game and adversary knows everything. But if you play this game with this maximum achievable quantum strategy, then you can, on one device, you can get at least 1 bits. And so this green graph was known in the literature. In my recent paper, we actually made a slightly modified protocol in which you can not only get this, but you can securely get these two graphs also. Okay, so now with my work, it's possible to get sort of this linearly increasing graph. So the randomness that you get is a linear function of this graph, and what we know is that this is the maximum you can do. So this is the maximum device-independent randomness that one can achieve as a function of this game. Okay. So yeah, so this was my work. Okay, so just to conclude, there is ongoing work in device-independent randomness protocols of randomness expansion protocols, meaning that people are developing different protocols, looking at different non-local games, and seeing if they are better or they're more efficient. There is a lot of experimental work going on, including like certain groups in China who have actually successfully demonstrated how you can do device-independent randomness expansion. And then there are related questions which are basically on the same principles of device-independent quantum cryptography, device-independent randomness amplification. The question that I was telling, I briefly addressed earlier, of how, if you have a source of weak randomness, how you can amplify it and use that amplified randomness as your initial seed for this device-independent randomness expansion protocols. There are like lots of different device-independent protocols being developed in the market for like different cryptographic scenarios. Yeah, thank you.
Thank you.
Hello.
Yeah, sorry, my foot did mute. Yeah, thank you for your talk, and also the slides that you have made are very appealing, I would say. And
thanks.
apart from that, your talk was also very enlightening.
Thank you.
So I think Muthu had some question.
Yeah, Chetan, actually. So I was wondering why the game rules are designed in that way. I was thinking that it was prisoner's dilemma. If you're not aware of it, let me explain. Imagine there are two players, and they committed a crime, and the police investigating both of them. So they have to collectively cooperate so that they can get away from the problem. So if one of them confesses, other person will get more punishment. If both of them confesses, they will get a minimum punishment. If they were silent, they can get away with the crime. So these are the game rules. So I was wondering the game rule that you have proposed is some modified version of prisoner's dilemma, because previously I have attended talks where people try to improve the probability of getaway with quantum. So they designed this game rules in such a way with the prisoner's dilemma to improve the probability of getting away from the crime actually. So have you thought of it before?
No, actually, I am not sure. I'm not even sure if they're the same game, because thinking on the feet, on my feet right now, they sound slightly different, but I can't. But I'll definitely look into it as to whether you can make a non-local game out of. As you say, that people are doing it. But this non-local game basically comes from the idea comes from Bell's theorem itself. So this was like this thing, a fact in physics. Which is sort of, it's just been rebranded or in such a way that you get a game, and a lot of computer scientists are interested in these games because they have certain games in computer science which map directly to games here. I mean, this is a very information theory way of looking into it, and I think it's easier to motivate.
This is more simpler to teach or explain anyone entanglement rather than using polarization and all.
Indeed. I think it's easier. It's the rules are very easy to explain also, so it's very easy. And in fact, to prove that this is the maximum winning probability is 3/4, is also actually
the prisoner's dilemma also, like people try to the success probability using quantum entanglement and Bell's violation and stuff.
So do you know what is the success probability of prisoners?
I'm not sure. I attended this talk 2 years ago. I don't remember exactly, but I vaguely remember this part about prisoner's dilemma and how
they might be the same. I'm not sure. I'll actually have to properly sit down and check. But thanks for pointing out. I'll check that out also.
And Swastik also has some question. Sure. Swastik?
Can we do one-to-many?
I think he has some issue with the mic.
Yeah, I think he asked, can we? Let me check. It's like
communication.
One-to-many communication using quantum cryptography. So meaning that there is Alice and n bobs,
Yeah.
Yeah, I mean, I guess there's nothing preventing.
Yes.
Yeah, there's nothing preventing.
Can you do it?
Yeah, there's nothing preventing Alice doing talking to multiple bobs. Yeah, you can.
KG has some questions.
Rutik, it is a great session. I had one question. By the word device independence, is there any connectivity or possibility of leveraging edge computing for this technology?
Leveraging what? Sorry?
Edge technology. Edge computing.
No, I'm not sure actually. I'm sorry.
We cannot use that edge computing.
I'm not sure of what it. Yeah.
Okay. Actually, it is a kind of utilizing a single board computer or low quality systems or low capability systems nearest or pervasive or nearest to the computing requirement, like in the healthcare or in the automation. There we can employ the edge computing. There will be cloud computing. The major portion will be the cloud computing, but the necessary computing requirement resources will be in the edge system. Then the process will utilize that one. That is the edge computing. I'm seeing the potential of utilizing edge computing, like in the form of FPGA or what is our Arduino or Raspberry Pi, these kind of devices as a co-located or pervasive environment. We are able to. That's what coming to my mind, but I'm not sure because this is also new to me. So I thought of okay.
Yeah, no, I'm sorry. I have not looked much into like computing.
Maybe
So yeah.
someone in the meeting, they may know that they can explain or they can share their idea.
Yeah, I'm sorry.
No, that's good. Thank you.
Thank you.
Yeah, Anand. Yeah, thank you, Anand, also for joining. Yeah.
Thanks, Rutvij and Chetan, for nice talk, and Chetan for arranging it. I have to leave for something. I informed Chetan earlier.
Yeah.
So I will catch you guys later sometime.
Sure.
Thank you.
Thank you.
Okay.
Yeah. So he's from Manipal University.
I see.
Any other participants, if they have any question or if they want to say anything, yeah, feel free. Okay, so I think also your talk was very enlightening. I mean, it was very something which a non-physicist also, I think, would understand. I mean,
Yeah. I mean, yeah.
it only comes after gaining that much expertise in that particular subject, and you have thought through things, then only you get that.
Thank you.
Yeah, thanks for joining also on a short notice, I would say.
No, thank you.
Yeah.
Thank you.
Okay. Okay, then I'll cut the call. And
Yes, thank you. Thanks. Thanks,
it will be
Chetan.
available on YouTube also. Yeah.
Yeah. Thanks, Chetan, for organizing. Yeah, it's nice. Yeah, thank you. Thanks a lot.
Thanks. Yeah, KG, I will try to.
Yes, Chetan, this is enlightening. Thanks a lot.
I would say Muthu can enlighten us with his new achievements recently that he has got.
Muthu is near to you. Muthu can. Indeed, if you plan, you both can meet either there in your place. Yeah.
Yeah.
Great. Thank you.
Okay. Yeah. Thank you.
Thank you.
Bye.
Bye. Thank you.